Our next talk is titled DDNeRF, Depth Distribution Neural Radiance Fields by Dadon, Ohad, and Yacov Hel-Or.
Good morning, everyone. My name is Dadon from Reichman University, and in this talk I will introduce DDNeRF, Depth Distribution Neural Radiance Field. This work was done under the supervision of Ohad, and Yacov Hel-Or from Reichman University, and was presented 2 weeks ago in WACV. So we start with a short NeRF recap. NeRF stands for Neural Radiance Fields, which is a neural network model that learns the implicit representation of the radiance field of scenes. The training data is a collection of RGB images, together with their camera parameters, and the task is to synthesize an overview of the scene. And as you can see, the model achieved very good results. So how does it work? We train a neural network model to map a 5D input into a 4D output. The input contains the X, Y, Z spatial location and theta phi view direction, and the output is the RGB color with the sigma, which represents the density at this point. Now, you can see that, So you can see that given enough samples and queries on the ray, we can use ray matching to approximate the pixel color and compare it to the ground truth pixel. This process involved the calculation of alpha, the transparency of the samples, which is calculated with respect to the sigma, and the density, and the delta is the length of the interval affected by that sample. From now on in this talk, we omit the sigma notation and refer directly to the transparency alpha notation. We do it to avoid confusion with the sigma in our model that represents the standard deviation of the predicted distribution. So how do we sample and train the model? Most of models use a two-stage hierarchical sampling technique that works as follows. First, uniform samples are taken along the ray. The model predicts the color C and the transparency alpha for each interval. Those transparency values can help to calculate the influence for each interval on the final pixel color. Those W values can be normalized and interpreted as a discrete PDF. And the final color is calculated using ray matching. The second stage, which is also known as the fine stage, is taking sample with respect to the first stage distribution. And the rest of the process is quite similar. We can interpret also those W values as a discrete PDF, and ray matching, using ray matching to calculate the pixel color. One more thing before the loss function, due to the fact that the second stage takes samples in more informative area, the output of the second stage is much better than the output of the first stage. The output, I mean the rendered color. And the loss function is a simple L2 loss between the ground truth color of a pixel and the approximated by the coarse and the fine networks, the approximated pixel color. Because the entire process is differentiable, this loss function and this process can help the model to learn the right representation of the radiance field of the scene. Despite the good result, this model still suffers from two main limitations: high computational demands for training and inference, and decreased performance in complex scenes, especially for 360 degrees real-world scenes, bounded and unbounded. You can see here an example for MIP-NeRF output on one of the Tank and Temples datasets, unbounded scenes, and you see that it's not very good results. MIP-NeRF is one of NeRF version that was developed by the same original authors to deal with the aliasing cause when rendering images in different resolution. Okay, we compare our model to MIP-NeRF most of the time. When analyzing those limitations, then we can see that for n samples, the depth resolution of the model is limited to 1 over n squared times the scene depth. which goes one of the two options. If we use too few samples, it leads to insufficient depth resolution, as you can see here. And when we use enough samples, it goes to large computational demands and many zero contribution samples. By zero contribution samples, I mean samples that have zero gradients due to the prediction of zero density at those spatial locations. But because the sampling process that we described earlier, we still have to take those samples. So DDNeRF. DDNeRF is a general extension for the existing NeRF models that produces a more accurate representation of the density distribution along the rays. Our main contribution is allowing the use of fewer samples during training and inference, and produces better output quality, especially for complex scenes. See this plot again. So DDNeRF refined the above distribution by predicting the internal Gaussian distribution parameters for each interval. It's allowed DDNeRF to take more accurate second stage samples, that lead to more efficient training and inference process, and to better output quality. Our architecture is based on the MIPNeRF architecture. The location input is encoded using IPE, which is integrated positional encoding, and the direction input is encoding using standard positional encoding. We add two additional linear layers at the end of the network to predict the mean and the standard deviation of the distribution. And note that despite the entire density in a section does not depend on the view direction, its entire distribution is dependent on the view direction. That's it. So how we represent this final distribution? After predicting the Gaussian parameters for each intervals, we truncate those Gaussian inside the interval bounds, ended up with one truncated Gaussian per interval. Gaussian weights are calculated with respect to the total transparency from the interval to the camera, and the final PDF is defined as a mixture of truncated Gaussian. We truncate the Gaussian because the intervals pass through the network independently with each other, so we don't want the distribution of one interval to affect or be affected by other intervals. It also, the truncation process also helps us to calculate the fast and the efficient probability functions, the CDF and PDF of this distribution. How the model learns to predict the distribution. So the coarse model is basically trying to mimic the fine model predicted distribution. We use scale divergence between those two distributions and add a regularization term to avoid overshrinking of the Gaussian and control the convergence rate. The overall the distribution estimation loss component is added to the standard NeRF loss that we described earlier. And this is a comparison of the training process between MIPNeRF and DDNeRF with 8 samples each. You can see here the blue dots are the coarse samples, the purple dots is the coarse samples, the fine samples. This yellow rectangle is the ground truth depth, and the blue curve is the distribution, the model estimate. So you can see DDNeRF produces more accurate representation of the density distribution, which lead to more precise second stage samples and to better output quality. So you can see the details here in the picture. And also note how DDNeRF distribution keep refining through the entire training process, while MIPNeRF distribution remain relatively static from an early stage. We tested our method on various domains using different number of samples. And as you can see from the table, models that use our extension outperform the baseline models in all cases. So quantitative example, this is the easy scenes, forward-facing scene of 360 degrees with a different samples number. Start with 8 samples. $16 samples. And 32 samples. And this is for more harder scenes. So the most significant gap in the result was observed in complex scenes, and especially around complex geometry region. You can see the bumps on the tires and some of the small wheels in the background. For unbounded scene, we integrated our model into the DDNeRF++ foreground model, and the results have improved significantly. You can see here the woods and here. This is an example of a computational quality trade-off. The baseline is MIP-NeRF with 96 samples and 300K iterations. And you see here DDNeRF with a different combination of sample numbers and training iterations. And you can see that we achieve quite similar, even slightly better results than the baseline using only 1/3 of the samples or 1/3 of the iteration to training iterations. And this is a qualitative examples. And you can see we achieve slightly better results while reducing the training time by more than a half and the rendering time by a factor of 3. Conclusion, so we introduced the general extension for NeRF models that can potentially be integrated with many NeRF variants. It produces a more accurate representation of the density distribution along the rays, reduces the computational demands, and improves the output quality, especially for complex scenes. You are welcome to visit our project page. Our code is available on GitHub. Thank you.
Thank you, David. Any questions from the audience?
Hi, thanks for the great talk. Why did you use specifically a Gaussian and not other distribution? Is there a specific reason, or it's just easy to use a Gaussian? Yeah, is there a specific reason for choosing a Gaussian, or is it just that it's an easy distribution to approximate, or something like that?
We did not try the other distribution. The Gaussian was more the intuitive, and it works pretty well. We did try some other metrics to compare the distribution, but we stay always with Gaussians.
Okay, let's thank our speaker again.